by an interaction between Earth's magnetic field that's decreasing and the solar wind and the solar magnetic flux ion fields that create this interaction that create the ozone layer.
Okay.
And the ozone protects us from high energy ultraviolet C. High ultraviolet C will penetrate deeper into ice and melt it. Okay, so you got energy from above and below. And it's not typical regular heating, but it will convert from ultraviolet into thermal heat when it strikes the ground or when it strikes snow.
Okay.
Right? So most of the melting is from below. And the oceans, when it releases this water, superheated water, it's 700 degrees or more. So we have these events. We know that these vents, and they're 23,000-mile long vent, like a radiator across the mid-oceanic cleft, across these things like in the Arctic and elsewhere. Over 90% of the most active volcanoes are under the oceans.
Yep.
Right? And they're venting out tremendous amounts of water, sulfur dioxide, and all kinds of chemicals. That's why you have chemobacteria and other things.
Okay.
Now, here's where the aha came. Now we've got the proof. It wasn't conjecture that we've got this incoming object. We know it's not a planet. That's all foolishness. It's a planet with a gold atmosphere and all stuff. It's a dwarf star. And if you take technically the fact that we have 3 stars in our system, 74%, according to astronomers, of star systems are estimated in our galaxy to be binary. And when we use the broad definition of a star, it can be a dwarf star that never lit. It can be one that temporarily lit and when fizzled out. It can be a regular yellow dwarf like ours, or a bigger star that burns out pretty quick, like a blue giant or whatever that can burn out real fast. Our star is the type that lasts a longer time. And then we can have a large planetoid-like object that can give off more radiation and certain bandwidth than it receives. So if you look at Jupiter, Jupiter by that definition is a star because it gives off more X-ray and more infrared radiation than it receives from the sun.
Sure.
So Jupiter is a star, according to that astronomical definition, and the dwarf star that's approaching is also a star. Now, because we have a plasma universe, you have this heliosphere around the Earth, which is around the solar system, and it's what's called the Oort cloud, which is another belt of debris beyond the edge, beyond where Pluto is one of these Oort cloud items, right?
Yep.
And I think they called Sydna, which is. They thought Sydna is actually bigger than Pluto. Pluto has now been demoted to be kind of like an Oort cloud object, and Sydna is a bigger object out there, Sydna.
Yep.
Now, what happens is when an object approaches that has large mass, it perforates like a balloon this plasma field, which is positive, net positive outside the solar system, and the sun is giving off all of this negatively charged plasma in the form of the solar wind. And that plasma means you've got like a balloon. So it pops the balloon, and a spike of discharge plasma jumps across interstellar space in the solar system, and it can do all kinds of things. The first thing it can do is you can get a big mass solar ejection. Now, when we think this happened, the solar mass ejection was in October of 2005. And I went back and I've done my calculations. In October 2005 is when we think it happened because it was then, and I think a little afterward, there was evidence there were several mass solar ejections that occurred between then and December. So that by December, they actually created, NASA and the International Solar Scientists, astronomers, created 2 new classes of solar mass ejections, an X and an M class.
Yep.
That meant that the balloon was popped around that time, around the fall, early winter of 2005. And so that it entered what's called the external plasma field, the positive side of the plasma field of the solar system. Right?
Okay. Yep.
So if you talk about that velocity, and of course as it approaches the sun, its velocity will increase.
Yep.
Right? Because it's going to be yanked in by the sun.
Yep.
And then it'll whip past it and then head back out into space in a hyperelliptical orbit.
Yep.
Now it's approaching what's called below the ecliptic, which means it's below the plateau of the planets would circulate like a disk around the sun.
Yep.
So its effects would be expected to pull a plasma discharge from the sun below the ecliptic or below the plane of the Earth as it approaches, and so it's more likely to affect the southern hemisphere.
Sure.
All right?
Yep.
It also is more likely to induce a tweak, if you want to call it like a ping, like an electromagnetic pulse weapon, and that ping will kind of vibrate these jello of the Earth and these sliding pieces of interlocked and carved pineapple So they'll jostle against each other as the energy is released through the plasma of the Earth, which is like a Leyden jar, or absorbing all this plasma energy. And if it hits specific frequencies or a specific angle, it's going to make the energy release in certain plates first before it releases in others. And there'll be a kind of we call a coup contra coup effect, where it'll hit one place and then like South America in Concepcion, South America, and then it'll ping and hit the opposite side of the Earth, which is in China. So if you actually look at the areas where these big earthquakes are happening, it's a coup contra coup effect, where you hear bing, bing, almost like something bouncing around inside a giant ball.
Got it. Yeah, okay.
Right?
Yep.
So you have the energy bouncing around. As it bounces around, it's likely, if it hits the Earth, it's likely to bounce, and it may have a slight change in angle, but it's going to hit a primary area, then a secondary, like your head bouncing around inside your skull when you have a car accident, you bang your head and your brain is bouncing around, so you get a damage on one side and the contra coup on the other side.
Okay.
So you got these three spheres, the outer mantle and the crust. Then you got the lower mantle, which is a streaming ball of superheated plasma and nuclear reactions occurring. So in other words, above the iron solid core of the Earth, there's a zone of seething. The Earth is a nuclear reactor, okay? And in fact, if you go down and look at the magma and the content of the heavy metals and radioisotopes, say in Yellowstone Park, the reason why that super caldera is so darn active is because if you sample the type of material in the magma, it's an incredibly high concentration of uranium and radioisotopes that when the mass comes together, it gets critical, and it's hotter than just ordinary magma from the Earth.
Right.
You follow me?
Yep.
So in other words, all magmas are not created equal.
Okay.
The magma that is coming up in Hawaii is different characteristics and mineral content than the magma, a little different silica, uranium, whatever, than other magmas. And then the magma in Yellowstone is really radioactive. And of course, it makes sense. That's why the largest storehouse of uranium on the planet is in Saskatchewan, Canada, which is not far from that area. So Central and Northern North America have the largest concentration of radioisotopes on the planet.
Okay.
Okay?
Right.
So what we have is these converging cycles. So here's a sequence of events. We have fluctuating rain and sunlight, which is occurring now. In other words, the seasons are all mixed up. So it gets real hot, like I'm in California here. It gets hot for a couple of days, and then it dives and gets rainfall. The La Nina effect is volcanoes from the Galapagos Islands, 1,000 miles off the coast, in this giant chain of islands, like a radiator, pumping superheated water, and the oceans are turning over, driving moisture that changes the trade winds and the jet stream and pushes moisture toward North America, California, the West, and around the world, the Northern Hemisphere. And that's why we're getting so much rain.
Right.
There's a direct link. So rainfall increases, which is the primary cause of ice ages. Sulfur dioxide increases, which is a more important driver than methane or carbon dioxide. They're minor factors. The most important factor is sulfur dioxide. The second one is water vapor. And the third, which is not recognized, is cosmic particles and dust. Because cosmic particles act as a source for micronuclei to help form rain droplets. Right?
Okay.
So what we've got now is these events, which means crop failures. Long before you ever have, quote, an ice age, you're going to have fluctuating weather and rain when it shouldn't be, so crops will die, or drying, or drought when it shouldn't be, and then extreme rains in other times, which is what we're seeing. And then it'll start converting where you'll see, let's say, snow in the middle of the northern United States into the first week in July or something like that. And then a year, 2 or 3 years later, it'll be like the snow has not gone away by the middle of the summer. And then it'll start accumulating. And because the rainfall and the precipitation rate rises, it's been estimated that the rate of snow accumulation that happened in an ice age accumulated at 100 feet of snowfall per year and didn't melt.
That's a lot of snow, and that's kind of hard to believe.
Right. Well, that's actually what was calculated, that's the kind of rate of snowfall, 100 to 200 or more feet of snow per year that doesn't melt. And then, of course, when it packs down, it forms this massive iceberg overburden, And of course, if you got buildings there, they're going to get crushed in no time at all. And I know I've lived in Canada, so if you got 4 or 5 feet of snow or